we had data for the pendulum, which was 23 point, how many seconds was that? 23 point what? Now, this was for 10 oscillations, which means 2.33 seconds was the period. Now, at the same time, we have this uniform circular motion thing where we took a couple pieces of data. And the last one in my watch is 23.35. I don't remember what the first one was, but I'm sure one of you does. So are we happy in saying maybe 23.3 is good enough for that? We're going to divide it by 10 either way. So I'm going to sit with 2.33 seconds. I think we can say that they were pretty close, maybe 2.32. Now, the first thing you should do is you guys should take a moment and go back to last week's discussion where we talked about pendulums and simple harmonic motion, and see if you can't use that 1.397 meters that you all just converted and predict what the period should be for that pendulum. But before you jump into that, should we use 9.8 for this or 10 meters per second squared for this? I'm just going to look in the chat and see if somebody has a... So Kevin's saying 10. What else you guys got? So right now we're split 50-50. Well, and here's the thing. Although you guys are saying it doesn't matter, the difference is going to be 2%, which is not very much. And although 10 is easier math, we're doing a laboratory activity, or one where we have values that were definitely based on an acceleration of gravity that's closer to 9.8 than to 10. So I would encourage you to use the 9.8 meters per second squared here. I think it won't make much of a difference, but if we're trying to compare the experiment to reality, we should probably stick with that. So I'm going to give you guys just a few more moments, and then we're going to start looking at how the circular motion one is similar. All right, when you have finished your calculations, please put it in the group chat. No prize on being first, because that just means that the person who's lazy is not going to do it at all. Excellent. Yeah, that's what I expect. Somewhere around 2.37 seconds. All right, so I'd say that our experimental value is very much in line with our measured value. Now, here's where it's going to get a little more challenging. Back here at the pendulum, I don't see anything with mass in it. So I am hoping mass cancels out. And here's where the math is going to pick up. Problem number 3 in the homework is not about an object being in a pendulum. It's about an object that's in uniform circular motion. And although it's got similarities to the pendulum in that some of the measurements are shared measurements, what we have is an object on the end of a string like so, and it's going to be traveling around this circular path. And what we'd like to do is see if we can't figure out what the period of oscillation of this system is. Now, in the homework question, we're given specific values to work from. The length of the string is one of the values. The mass of the bob is one of the values. And this angle here is one of the values. And all of these are going to contribute. Now, noticeably absent the radius of the circle. Now, looking about this class, I know I've got a lot of my sharp kids who are here today. Is there a way that you can represent the radius in terms of things that we were given? Why don't somebody speak up and tell me? Or maybe I could do something. No, it's not going to be all over 2. But although I do appreciate your zeal to answer, Kevin, think about it for a moment. Do you see anything that could give us a method for calculating R? AJ suggesting sine, and I'm thinking I'm right there with AJ. That's right. R is going to be L sine theta. So when we contemplate this, we're not allowed to have R in our answer necessarily, but also if you looked out there, I never measured R, but I did measure the length. On the other hand, I did not measure theta, so we might have a problem. I have to go back out there and get a piece of data. Now, there's one more thing I want to point out before we get going with this. We know that this is going to be a uniform circular motion problem, which immediately suggests, as all of you, I hope, are getting to the grip of, we're going to have to do something with that. There has to be an unbalanced force, and the acceleration caused by that unbalanced force has got to be proportional to v squared over r. Now, we've been talking about this for the last couple of days. Although this is not a roller coaster question, it is most certainly a uniform circular motion question. So when we're considering how we're going to work this out, we are probably going to have to resolve forces. I can't see any way around that. But even before we look at that, I don't see anything about the period here. And I certainly didn't measure anything about velocity. So before we launch into anything about net force, we might need a strategy as to how we're going to figure out period from the information related to force. Now, this one might be tough, and I'm not sure I can expect to see a lot of you be able to jump at this one. I think over time I might be able to get it out of you, but we have limits to how much time we have today. So I want to remind you, this object traveling in a circle, it's traveling with a constant speed, and I'm pretty confident you guys can tell me what the perimeter of a circle is. So if I wanted to figure out a way of, relating the period to how fast it's going, I would hope you guys remember from first semester that for something traveling in a circle, we have a way of relating how fast it's traveling to the perimeter and the period. And this is old. We're talking first semester when we're doing orbits, but still quite relevant. So I think we have all the tools we're going to need to work this out. But like I said, there's going to be some math here because we're going to have to resolve forces. So the first thing I want to do, since I do need to resolve forces, is I'm probably going to put together a coordinate system. One of the things you've always been encouraged to do whenever we have to resolve forces is to consider what coordinate system we're going to use. And I think a coordinate system lined up with the radius makes the most sense. Remember, for anything dealing with uniform circular motion, we have to find the net force in the direction of the center of the circle. So along the x direction is along that direction. But I only have two forces here. There's going to be tension in the string and weight. Now, this part shouldn't be tough, but I am going to have to deal with the fact that only one of these forces actually has any components that are in the direction of the center of the circle, and that's the tension. In fact, when I look at this, I see very clearly that I'm going to have a component of the tension upwards and a component of the tension towards the center. And this will form my triangle that I'll use to figure out the size of each of the components. Unfortunately, I'm going to need this angle to do so. Now, is that angle the same as theta? Give me a yes or no in the participant window. Having a little bit of contention here. We're at 10 to 2, 12 to 2. Wow, we're really kind of piling on that yes number, aren't we? If you guys are so smart, does anybody remember what the geometric theory is that would say why those two angles are the same? That would really impress me. There it is, alternate interior angles, that's right. Good job. I can always count on 7th period to know things. I can't always count on that all day long. So, and yeah, that's right, Kevin. When you get the right answer, it's okay. Now, this next part, we know t cosine theta here, t sine theta here. And I know on your phones that's probably a little small, but we've done this problem many times before, so I don't feel too compelled to have to go through it with you a lot. We've had this exact arrangement before. So our next part is to take our net force problem, break it up in the y direction and break it up into the x direction. Recognizing that in the y direction, the net force is going to be 0. The bottle didn't fall to the ground. But in the x direction, we're still stuck with mv squared over r. Now, there were two forces in the y direction, t cosine theta acting up and weight acting down, which gives us a clear way of figuring out the tension. Now, this is important, I think, and you might not see why it's important, but did you guys see me measure the tension out there with my tensionometer? That's right, I can't measure that. I could measure the mass of the water bottle, and I'm hoping I don't have to because I didn't. And more importantly, but I know there's nothing here with tension in it, so I'm going to intentionally try to cancel out the tension. Which is why in the x direction, I know I have tension, t sine theta, which is going to equal m times v squared over r. Still going to have to deal with that v squared over r issue. So, the first thing I hope you guys recognize is that we can eliminate tension between these two. And that will get rid of the tension, which is something we didn't measure, and hopefully keep us focused on things we can measure. So I'm going to solve this side for t. And now I can make my substitution. Now here's where things are going to get a little bit cumbersome. I have mg times sine theta over cosine theta. I'm going to group this, and I know there's one of you out there who's going to tell me I should convert that to tangent. The reason I'm not going to convert it to tangent is because, wow, you guys in the chat, man, you're going to have to take it down a notch. We're all friends here. Of course, in class, I would just say have at it, but, we're all friends here. Maybe not. But it doesn't matter. We're all in school together. We're all pandemic friends. We'll just say it like that. We're pandemic friends. Now, the reason why I'm not going to go and reverse this down to tangent is because I'm looking to the future and realizing that eventually I'm going to be substituting in r that has a sine in it. And so I'm afraid that if I have tangents and sines, it's just going to make it harder. If anything's going to cancel out, I'm going to want to see it. So I'm going to leave sine over cosine there. But on the other hand, I think it's at this point where I can start making some substitutions, meaning I don't want to leave velocity there. I'm pretty sure I want to start writing something in terms of the period. I mean, let's face it, it's 325. We'd like to zoom in on the end of this, right? So let's start with that. And I'm going to bring the r in front of, put that underneath that m so that all I have in here is the v squared, which is going to be 2 pi r over period. Make sure you're good for that because the paper's getting pretty cumbersome. I'm probably going to go to a new page here in a minute. But before I do, you do see that we get to cancel out the m's, and it looks like I'm going to get to cancel out one of the r's here in a minute. So I'm going to go to a clear page so that I can write a little bit bigger, and I can also maybe make the rest of the algebra a little clearer. Okay? So here, I could write, that this is the adjacent side, but I never measured that. Go g sine theta over cosine theta. And on this side, I will have 4 pi squared r squared over rt squared. And check your work and make sure my algebra is good, but I'm pretty confident in my algebra. And I'm confident enough to go ahead and cancel out that one r I knew was going to cancel out. Good so far? Not too crazy? Because we still have that r that we can substitute in with L. And once I do that, the only thing left are things I can measure. So I'm going to go ahead and do that. G times sine theta over cosine theta. God, this is really complicated. Equals 4 pi squared divided by t squared L sine theta. All right, well, you see why I didn't want to cancel out or convert that to tangent, right? You do all see that one of the sines cancels. And I can do that. And as you might have guessed, I'm going to try and get t by itself. So the next thing I'm going to do is multiply both sides by t squared. So I can cancel out that t squared in the denominator. And now this is kind of a mess, so let's kind of rewrite it a bit. So I'll have t squared g times 1 over cosine theta equals, well, 4 pi squared L. Eesh. It's getting close. I'm going to go ahead and put this stuff on the other side by dividing by g and multiplying by cosine theta. Now, if you've really been paying attention from the very beginning of this, you probably realize that our goal was to get something that looked a lot like this is looking. Right? Square root of both sides. And when I do that, I actually get, something that looks more like 2 pi times the square root of L over G. Man, that's close. That's real close, isn't it? But unfortunately, it's just not close enough. We've got this cosine theta in here. And there's no way for me to get it out easily. I mean, if I look back at the picture, it's just so nice that this looks so close to a pendulum. I kind of want to ignore that cosine. But you guys who are the math types, all you mathletes out there, would give me a bunch of, grief about it. On the other hand, I know that anybody in this classroom who had a 79.98 would be just assuming I'd make that an 80. Am I right about that? Like if at the end of the quarter you had a 79.99, you would just assume Mr. Shelton would round up to an 80. Now I know the math classes, they don't do that. You're not getting away with that in the math class. But we're in physics now. Now, you might be wondering why I'm saying this, but here's what I want you to do. You have your calculators, right? You might not remember the small angle theorem from a couple of weeks ago, but I would like you to take the cosine of 10 degrees and tell me what you get. Wait. Before you get all excited about that, remember, you're taking the square root of it. So before you start throwing numbers, maybe take the square root of that cosine of 10 degrees. Oh yeah, now do you see why I might have said something about what happens when you get a 79.99? Because as long as the angle is small, this number is actually really close to 1. Was the angle I used for our experiment pretty small? I'd argue it was pretty close. Now I'm bringing this up because I think you guys need to see that even with the pendulum, we had to have a small angle approximation. If you look back at your notes, you should see it there because Pendulums aren't perfect harmonic oscillators, and neither is this. But they both are very close to the same shared value, which is why we get the same period, both for the one that rotates and the one that acts like a period. Now, there was a lot of math to get here, a lot of math. And I don't expect the AP exam to really have this level of math on it. But I also expect you guys to be capable math students, which is why this was a worthwhile exercise and why I feel like now you should have no trouble answering A, B, and C for question number 3 on your MyAP, which is what this is all about. It takes this problem and breaks up into steps, and we'll step you through it, but now you've seen the whole problem from beginning to end. Now, we're done with our mathematical portion of the lesson, our physics portion of the lesson.